Bien. Muy bien. Okay, all right. So sorry for the delay. We had some unexpected technical problems, but finally we are happy to introduce Alejandro Gómez, who's going to, well, to be the first after the summer break in our online seminar series in Quantum Spain. So very happy, Alejandro, that you accepted our invitation. So let me shortly introduce him because I don't want to delay this more. Alejandro studied here in my university in Santiago de Compostela, and then he went to Queensland in Australia for his doctorate. And he has been working in the development of qubit and resonators, superconducting resonators. Then he moved to Finland, and he's a senior quantum engineer at IQM. And he started working at the coherence improvement team. Now he's in the QPU control department. Working in calibration topics. So he's going to give us an update of the status of the development of what he's doing. And well, without further ado, Alejandro, thank you. And the floor is yours.
Thank you very much. I hope everyone can hear me well. Okay, so I'm Alejandro. Just thank you for inviting me. It is actually amazing to be able to participate in such an event. And I will be discussing a few of the recent accomplishments that we have shown to the world regarding our cloud quantum computer. So I guess let's just get started. So first, I'd like to kind of showcase a bit what our company is trying to give to people. So we have both on-premise and cloud quantum computing offerings. So you can have, for example, a computer at your university or HPC center that you just have locally, maybe connected to the rest of the HPC infrastructure. But we also support some cloud offering of specific QPUs, which is a bit of a more affordable kind of provider. And we also have kind of different architectures that we allow people to use. So one of them is this IQM crystal architecture, right? So this is a multiple qubits that are connected through tunable couplers to each other's. And it has a advantage of a kind of okay connectivity, but very fast parallel operation. So you can do gates on many devices very quickly. But we also offer this IQM star architecture, which is a bit different. Essentially, what it tries to do is it tries to provide one-to-all connectivity. So you can do, in principle, gates for basically entangle qubits that are far away in the device through this common element called the computational resonator. I'm going to be mostly focusing on the IQM crystal family, since that's the one that we have this larger device available right now, but I wanted to just kind of showcase that we're working on several parallel architectures at the moment. So basically, our QPUs are built from certain elements. One of them is a tunable transmon. So basically, the tunable transmon is a superconducting qubit that is made from a squid. For those that might not be aware of it, squid is a superconducting quantum interference device made of essentially two Josephson junctions in a loop. And you can see on the left, you can see basically what the circuit model for this device would look like. It's just, again, this squid with a parallel capacitor. And then you also see a SEM microscopy image of the one qubit. So basically, it is very nice because it is an anharmonic oscillator of sorts. So we can address the different computational states independently. And that's kind of one of the nice things about the superconducting qubits, that we can design them to be however we want. In general, we are not limited by natural properties of, for example, ions, etc. In terms of the superconducting qubits, depending on, again, the squid has two junctions, let's call it A and B, right, or 1 and 2. depending on the ratio of the energy of the Josephson energy of those junctions, we can change the tunability of the transmon. Basically, what is the transmon frequency as a function of applied external flux? So for a fully symmetric squid, you see that you have, on the left, of course, you have a lot of tunability over like several gigahertz in frequency. While on the right, you have the case where you have either two separate of a Josephson junction energy or a single junction, in which case you basically have no chance of any tunability at all. It's going to be a fixed frequency transmon, which is relatively common in the field, I would say. It's only recently that tunable frequencies have been applied at such large scales, I think. And in the middle, you have a intermediate case where the Josephson junctions are somewhat similar in order of magnitude, but they're sufficiently different. And that reduces the tunability range in frequency space. And in general, this is a more realistic, I think, model, at least for shorter term devices. I hope that in the future, these things will improve. But for now, I think this is a realistic model that we have to work on. And if anyone is curious, I generated these images using this SC qubits package, which is open source on GitHub, and you can use it to study different qubit architectures, different parameters, etc., etc. I think it's overall it's quite handy for these very short checks and stuff like that. And I would like to kind of also explain maybe how we are doing our gates, kind of briefly. I'm not going to go too in depth into it. But as you can see on the left, what is the Hamiltonian of a single qubit that is driven by some time-dependent poles. And after doing a few transformations to kind of get into a more appropriate and easier to calculate frame, you end up basically saying that these arbitrary poles, really what it does, it generates rotations on X and Y axis of the Bloch sphere. Of course, this is only if the drive is resonant in frequency with the qubit. If it's not, then you will basically see nothing at all. And there's one caveat here, and is that the transmon is actually not a pure qubit in the sense that we don't have only two computational states, but we have an infinite manifold of them. So it is very possible, and actually it happens quite a lot, that if your pulse is not well calibrated, you will have leakage to non-computational states. And this is unwanted because it always reduces the fidelity of our operations. So we're always looking into ways to avoid this. And one way that already has some, a few years ago, it was already like described is this drag pulse, so derivative removal by adiabatic gate, which basically says that if we do the in-phase component to be a Gaussian pulse, and the out-of-phase component of the pulse to be its derivative, then if you do all the calculations, you have a way to really reduce the leakage to higher states. Of course, this is nice, but it's, as always, approximations at the end of the day, so it's not enough. So we are also working internally into like improving, reducing really the leakage in a way by choosing more smart or new kind of pulse envelopes, like the higher order derivative of the drag. So you add more and more derivatives to the out of phase component, for example. And also we can do virtual set rotations, which I think in general can be done very cheaply because it's just a change in the pulse phase in the hardware at the hardware level. So it really takes no time to do that. And that's kind of the basics for the single qubit gate. I would also like to explain now that our qubits are coupled by this coupling structure, which we call the tunable coupler, right? You can see here both the circuit model, but also the SEM image of what it looks like. This was already shown in a paper a couple of years ago from our company. And maybe I'll spend some time here explaining what the different things are. So on the left, we have qubit 1 that we saw before. It's the same image. And on the right, we have qubit 2 in orange. Qubit 1 and Qubit 2 both have 3 different types of lines going through them. One of them is the coupling to a readout resonator, which we basically use to read out the state of the system by applying a microwave drive to it. You also have the purple line, which is the drive line, and that's the one where we are sending the microwave pulses to modify the state of the qubit. So the one that we just saw a couple seconds ago. Finally, we have the flux line. So the flux lines essentially accept flux pulses. So an AC current essentially goes through there. And so that AC current will generate a magnetic field that crosses over the squid loop, and thus it generates a flux that allows us to change the qubit frequency as we saw before. Now, you might ask, what is that thing in the middle? Well, that big structure in the middle is the tunable coupler, as I said, and it is just basically another transmon. The shape is a bit different because it has these waveguide extenders that allow us to couple qubits that are very, very far away. It might be hard to see from this picture, but these qubits are basically millimeters away, which at the scale that we're working on, it's a huge difference. And by changing the flux applied on this coupler, basically we can modify the effective coupling between the qubit 1 and qubit 2. Our 2 qubit gates then are done in a kind of similar but slightly different way. So on the image on the top left, we basically see the simulation of what the coupling between qubit 1 and qubit 2 is as a function of the frequency of the tunable coupler. This is not so important right now. The important message here, I guess, is that because of this design and because of how we set up the parameters of our device, we can effectively cancel the coupling between the qubits. That's a regime where we are extremely close to zero coupling. And that means that we can basically have our lattice of 20 qubits such that they are basically uncoupled from one another. When we want to do a 2 qubit gate between a pair of qubits, then we put 2 of the excitations, so 2 of the transitions, the 1-1 state and the 2-0 state, close to resonance. So we do this by, again, applying a flux pulse on the qubits. And then we turn on the interaction by modifying the frequency of the coupler. And that will basically accumulate some geometric phase on the 1-1 state that will, if well calibrated, generate a pi phase accumulation. Just a bit of a small note is that we are using Slepian pulses. So the Slepian pulse is essentially one of the optimal shapes in terms of the energy per frequency applied. And it's a kind of semi-new technique that was used, that basically was inspired by some signal engineering developments. Now one might ask as well, how do we do these gates in parallel, because we cannot you cannot use all of the qubits at the same time to do 2 qubit gates. So our solution to this is to do edge coloring, which I'm not going to go into because it's a complicated mathematical framework, I think, to explain in a few minutes. But the point message here is that we can separate the pairs into either 4 or 8 parallel groups that we can apply 2 qubit gates on. And we found that actually using 8 groups instead of 4 is typically as good as if we were doing the gate by itself, with essentially almost the same performance, but using a lower amount of groups, so more qubits in parallel being addressed at the same time, then our performance was reduced quite a bit. So these are the kind of building blocks for our QPUs. And right now in the square lattice family, so the IQM crystal family, we have currently these 4 types of devices. We have the IQM crystal 5, which contains 5 qubits and 4 couplers. That one we can produce at scale, and it's actually one of the devices that we also provide as IQM Spark, which is one of the on-premise devices. There's the IQM Crystal 20, which has 20 qubits and 30 couplers, and that's the same one as we have on the cloud. Then we are working now on putting this Crystal 54 in the cloud as well. It's still going through acceptance testing before it can be there. but it has 54 qubits and 90 couplers, which again, it's like 140 different transmons in one chip, which I think personally, it's already like quite a big accomplishment. And we are also preparing the work for the 150 qubit, which will have like 266 couplers in this, which I personally find incredible that we can do this type of things, but it is a reality that we are working on it. Just quickly, some photos of the different chips. Note that the Crystal 150 it's only made. It's just a like computer generated image. It's not a real one yet, but all the others are real images of our devices. In terms of hardware, our quantum computers are designed such that they can fit in with standard HPC equipment. So they're not going to be like extremely out of place in a typical HPC environment, essentially. We have designed our own in-house electronics in order to squeeze as much performance as we can. But there are certain things that we cannot do ourselves. So we go for commercially available products. So the most, I think, important one is the Blue Force dilution refrigerator, which you can see one of them in this image, which is extremely important because these devices have to, in order to work well, they have to be extremely cold, like 10 millikelvin or so, which is what, like 100 times colder than outer space, something like that. And we also get, for example, DC modules from Qblocks and some other providers. In terms of cryogenic hardware, we also have quite a few of our internal designs, but we also get from different providers. So this is just an image of the lowest stage of the dilution refrigerator. You can see the QPU also space for a parametric amplifier, which is just a quantum limited amplifier that has to also work at very, very low temperatures. Isolation, you have attenuation, you have all sorts of things that are required for the QPU to stay cold but operable as well. And also, of course, to be able to reduce the noise and all sorts of things. It's quite a complicated design as well that I'm not going to get into too much. I think the important one thing to mention is that most of the components are made from high purity and gold-plated copper, which provides very good thermal conductivity, so the heat can be transferred very quickly from this bottom part of the refrigerator to the outside. And also it prevents oxide growth in between the layers, so there's not going to be any bad thermal connection between different components. I will also, our software is also part of the whole thing, so I'll also mention it quickly. So our software is internally made in-house software. There's very few parts of our software that are currently open source. So we have at the bottom our hardware, so qubits, all the instrumentation required. We have a layer that basically has drivers and firmware for all of the instruments that we need to access. And we have a generic composition layer, which is what we call station control, which transforms the information that for all the cases that we want to execute into the physical pulses, with also including all the calibration data from the engineers. And then we have all the top layers, which are Cortex and Exa, and also adapters from popular languages like Qiskit, Cirq, and OpenQASM into Cortex. So you can just write whatever circuit, whatever algorithm you want to execute in our computers in a higher level language that is very common. Again, I imagine that Qiskit and Cirq really are the most common ones, but there are all sorts of them going on around, and more pop up every day, it seems. And we also have Exa, which is essentially our experimentation software, which allows engineers to develop really physics experiments that can be used for research, but also for calibration. I put here like a bit of a code snippet on how you would write a Qiskit circuit and execute it on one of our backends. Just so you can see that there's really not much that you need to add in order to execute it. It's made so that it's very easy to interface with existing user workflows. We also have the problem that we need to keep our quantum computer well calibrated over time, and we need to automate our operations and stuff like that. So the solution that we have come up with in order to keep our computer calibrated is this directed acyclic calibration graph. It's called a DAG, which basically has nodes that are calibration experiments and dependencies between them. So in order to run experiment 2, you first need to run experiment A successfully and stuff like that. This software allows us to go from the design parameters that all of the design and simulation teams provide. And with those parameters, we can generate a system identification. So we can figure out all of the Hamiltonian parameters of the system, and we can then calibrate our gates using those parameters, and finally run different benchmarks to check out what is the quality of our device. Thanks to this, we can also have relatively quick periodic recalibration to make sure that there's always going to be a calibrated device before you run any circuit. And it is somewhat dynamic in the sense that depending on the results of the node, it might choose to do one action or another. All of our nodes are also created using knowledge and experience from lots of very smart quantum engineers. And so there are really, really high quality thought processes going on here. And it also is capable of automating research workflows such that maybe people can be able to even understand new physics by doing this. But yeah, now that I kind of went through the preliminaries, I would like to maybe discuss a bit about our benchmarking now. So we benchmark at different levels. So we have, of course, applications. So we want to benchmark how well we can run an effective circuit for some problem that we want to solve. We have also fundamental physics issues. So for example, how good is our entanglement between our qubits? Then we have benchmarks at the system level, basically how good are operations of multiple qubits working together. And this is typically done through this rectangular gate-based benchmarks we'll discuss in a bit. And finally, we have to also benchmark our foundational operations. So the quality of our qubits, the quality of our individual operations, and also the crosstalk in both microwave drive and also flux. I think this is maybe a good point to do some questions if you guys want, like quickly before we move on more specific descriptions of the benchmarks.
Yeah, I also put this in the chat. If anybody wants to stop and make a question, just raise your hand and I will activate your microphone. Yeah.
Okay, I don't hear any questions coming, so maybe I'll move on. Please feel free to interrupt me whenever you want to ask anything. So first, let's talk a bit about the foundational operation. So there's a few things here, but the most important is the crosstalk. Essentially is, let's say you have a few qubits in this grid. You want to address one of them with, let's say, a single qubit gate to simplify things. And we want to figure out what is the effect on neighborhood qubits, or even faraway qubits. I think we can show here in this graph that actually our crosstalk is relatively low. I think basically the median drive crosstalk is around -50 dB. And the median flux crosstalk in this device is around -70, which I think is extremely low values. So you can guarantee that at least neighboring qubits are not going to really affect much the quality of your gates. And there's also the simultaneous readout error. So you're able to read out all of the components simultaneously. And I think the median right now is close to like 2%. We are trying to make it lower, but right now in this device, it is what it is. And another important metric is really the coherence of the device. So how long can we keep a quantum state coherent? And I don't think I'm able to reveal for this device right now what they are, but for our test device that we use to really benchmark how good our fabrication is, we have seen T1 times of even close to 1 millisecond, which we hope that this type of very, very high values can be translated into our main offering soon. But really what we are going to do is benchmark through executing circuits. And the major way to do this is benchmarking through randomness, really. So what we want to do is we want to investigate what are the imperfections of our gates due to the noise channels of the system. So again, imperfections, over rotations, under rotations, all of these things that are very, very bad for operation. The way that people have thought about this is that we basically execute random circuits by sampling from some uniform distribution of all the possible unitary transformations that we can execute. And mathematically, if you do all the calculations, it turns out that this averages all the different noise types or channels into a single mathematical form, which is a Pauli channel. And there's one problem here is that there's actually an infinite number of unitary transformations that we can realize. And so it is actually not very efficient to do it this way. So another very useful mathematical property is to use this unitary T design, which is a finite subgroup of this group of unitary transformations that allows us to essentially get the same results by averaging over and over and over it. But we have to average over a very finite group now instead of an infinite, which is it's a lot easier. So the circuit that you see underneath, it's a circuit for what we call randomized benchmarking. So randomized benchmarking basically says we want to execute an effective unity transformation on our full quantum state, but we also want to see what the fate of running many gates is. So let's say we want to do C and its inverse, such that the total ideal operation would be the unity. We calculate C as several layers of randomized operations over our quantum state. And we know that these operations are imperfect, so we add these lambda error channels to them. And then we compute what the ideal inverse operation to this would be, so the C minus 1. And if everything went well, then our state will be kept constant over time. But because it's not ideal, then we will see an exponential decay in the survival probability of this state. And this can actually be related to the average error rate over the applied gates, which we are using. And this is this R here, which depends on the number of gates, D, that you are applying. So the number of random layers that you are using here, and also the P of this exponential dependence. So then we can use this randomized benchmarking, and in particular, we are using a variance of this, which is called the interleaf randomized benchmarking, which allows us to not only quantify what is the average Clifford gate fidelity, but also allows us to specify what the one specific gate is. So really, let's go to this diagram here. So on the top, you have what we just explained, normal randomized benchmarking. On the bottom, you have interleaf randomized benchmarking, which is apply one random gate and then apply the target gate that you want to quantify, another random gate, and then interleaf the same gate that you want to quantify the error for, etc., etc. So by doing this, we can basically at the same time get both our average Clifford error rate and also our average rate for the gate that we are trying to benchmark. So in our IQM Garnet device, we did this for all the single qubit gates, the C set, and also this basically the Clifford group C2, which is this 3 unitary design. And our error rates are quite low. So for single qubit gate, you can see that our median rate is around 1 in 1,000 errors. Our 2 qubit gate is close to, I think, like 90-something percent, 99 point something percent. And our Clifford is close to 99, is a bit lower than that. We also, of course, also run this on fundamentally test devices. And right now, our best device has a 99.9 C-set fidelity, which is essentially state of the art for this type of gate, which we are quite happy about. And again, we hope that we can also provide it for our customers in the future. As I said, we also want to do benchmarks that are a bit different, that depend on more things. So there's a family of benchmarks, which are these rectangular random layer benchmarks. So we get a layer that is rectangular, in which we have W qubits and D layers of random operations. And the purpose, one result that we know is that if we have an input, a random quantum circuit, and we ask it to generate a number of output strings, the ideal solution would, the acceptance, if 2/3 of them have some greater than the median probability, then we say that it has passed the heavy output probability generation problem. And that's just a mathematical problem that we can use to benchmark the quality of our square rectangular operations. So this is what is done in this quantum volume. So quantum volume essentially is you have a initialized ground state for all of our qubits. We do a random permutation of the qubit indices, and just so we randomize in which pairs the gates are being executed on. And then we apply a random 2-qubit gate on these randomized pairs. And we repeat this d times. This kind of scrambles the input and makes it so that we have this exponential probability. And then we see that we pass the heavy output problem within 2 standard deviations. And thus, the largest square circuit that we can execute for the same number of qubits is 2⁵, so 32 quantum volume, which is, I think, also quite high for the size of the device. We can also vary the width and the depth of the circuit. So instead of making them like purely square, we can make them rectangular. And this is the origin of this volumetric benchmarking, right? So volumetric benchmarking basically allows us to figure out what is the trade-off between having a larger depth of the circuit versus a larger number of qubits being used. And the reality is that for many NIST devices, you don't need to use as many qubits to do interesting things at the scale that we are right now acting. And thus, being able to quantify what this relationship between depth and width is, I believe it's quite important. And in the right here, you see the results for varying the width and the depth of our circuit. The squares that have a black border are actual data, and the rest of it is just extrapolated to try to quantify, because these circuits actually take quite a long time to execute. We also want to benchmark the speed of our operations. So there's this very nice benchmark that also takes a lot of time to execute. The circuit layer operations per second, the CLOPS. It's a bit complicated to explain. I'm going to try to do my best to explain it. So we basically want to see how many quantum volume circuits we can execute per unit of time. So what we do is we first prepare 100 templates of these quantum volume circuits, in which we keep the permutations constant, but we parameterize the 2-qubit gates by some parameters. We execute them one by one for, say, the first one for 10 different randomized parameters. Then we take the output of that and we feed it to the random number generator as a seed in order to generate the next set of parameters. And then by repeating this many, many times, you execute this, and then you just quantify these CLOPS here. And it turns out that our IQM Garnet has right now 2,600 CLOPS. And one may ask why you want to do this. And really is because this takes into account not only the quantum operation time, but also the classical to quantum feedback. So how quickly can we basically talk between our control classical computer and our quantum processor. We also want to benchmark what the entanglement in our system is. So this can be done through the GHZ state. This is Greenberg-Horn-Selinger state, which is nothing else but the generalization of one of the Bell states, in which you have all the M qubits in the ground state and all the M qubits in the excited state, and you have a superposition of those. So it's the maximally entangled, one of the maximally entangled M qubit states, essentially. So we measure this as well, and really the big message here is that we can have a generally entangled state of 20 qubits with error mitigation, but slightly lower if we don't do error mitigation. Finally, I want to talk also about a benchmarking a useful application. So Atos, which is a European company, developed this Q-score benchmark. The point of this benchmark is the following. So we first generate a number n of random graphs that we want to benchmark on. We execute a optimization problem using QAOA to solve the maxcut problem. The maxcut problem basically says we have these random graphs and we want to maximally separate them into two graphs of such that the number of edges in between the two generated graphs are maximal. And then you compute the CN, so the cost of this, which is the average number of sets of edges between these two sets for the n components. And basically, the QPU passes this test if this beta of n score is larger than 0.2. So our Q score right now, our verifiable Q score is 15. So that means that we can do up to 15 nodes for this maxcut problem. And yeah, there's many benchmarks. So let's do a quick summary. So randomized benchmarking, we estimate the error of our gates. Gate set state, we estimate the largest entangled state that we can generate. Quantum volume, we estimate what is the joint scaling of fidelity and qubit count together and not separate. Volumetric benchmarking, we estimate what are the trade-offs between the number of gates that we used and the number of qubits that we use. The CLOPS is the operation speed, including classical quantum feedback. And the Q-score is the largest size of this successfully executed useful optimization problem. You can see in the right a summary of also the numbers that we got in case you want to take a quick look. And that is kind of the story of how we are trying to benchmark our IQM devices. Finally, I also want to give a quick overview of this IQM star architecture, which is slightly different, as I said. So it has a one-to-all connectivity through these computation resonators. The qubit resonator operations are going to be CNOT and move. So you can basically, you say you have an excitation on one of the qubit, you can move that excitation to the computational resonator. And you can also do a CNOT operation between resonator and the qubit, which will effectively, if you do a few of these, entangle faraway qubits. And one of these devices is available through IQM Resonance, and it's called IQM Garnet or Star 6. And you can access it through, again, IQM Resonance, and you can also get a nice tutorial on how this is used through IQM Academy. And I think I am finished here. So I think for conclusions, we can say that we have a mature 20 qubit device with tunable couplers, with state-of-the-art error rates and also speed, and that we characterize at different levels using different methods. And I would like to also acknowledge all of the 50+ contributors from IQM to make this possible. It's been a very long journey to get here, and we're only going to get better from now. And I also mentioned that all of our quantum computers right now are co-developed with VTT, which is a research center here in Finland. And yeah, you can access this device in IQM Resonance and also Amazon Bracket. And I think that's everything for me. Thank you very much.
Well, thanks a lot, Alejandro. Very, very nice, very clear. And I'm sure there might be some questions. So let me check in the chat if there's anything written. No. So please, if anybody wants to ask something, just raise your hand and I will allow your microphone. Yeah, I see here one. Mic, which is Juan Villasuso. Yeah, Juan, go ahead. Oops. Juan, wait. I think I enabled your microphone. I think Juan Villasuso. It's unverified. So I don't see. Wait. No, wait. Allow mic. I'm allowing. So the microphone should be allowed for you because it says. Juan, can you speak? In principle, one. No. You have the microphone allowed. Let me see. Maybe. Okay. So there's some. Well, sorry for this, but Juan has his microphone enabled as far as I can see. Yeah, it's strange. So maybe he didn't want to just raise his hand, but he didn't want to speak. So this 2-qubit fidelity is an average over many different 2-qubit gates, or is this for the basic is for the CNOT or for
Yeah, so the average 2-gate fidelity is typically reported for a single gate, which is the CZ gate in this case.
CZ, yeah.
Yes, and we also benchmark what is the average Clifford gate fidelity, which again, these Clifford gates are just the subset, a unitary 2-3 design of the unitary gates, right? And so in a sense, they are kind of a way for us to express, how to say this, all of the different gates that we can execute. And the unitary 2 design, so that includes 2-qubit gates, is always a bit lower than CZ, but it's also reported as something 98 point something, I believe. So we have both of them, like the general random one for all the possible gates, and also the specific gate that we have implemented as our native operation.
Yeah. Okay. So Sergio Jimenez is asking whether you consider these benchmarks scalable for other kind of qubit technology.
Okay. Some of the benchmarks are quite hard on the dimensionality, and it's hard to say whether they will be scalable at this point. I imagine that some of them might not be quite scalable. Quantum volume and CLOPS, I think, are going to be quite hard to execute after we are maybe in the 100 qubit threshold or so. I think that, for example, all the algorithmic benchmarking like this Q-score hopefully will be feasible to be executed in the future for larger and larger devices. I would say also that maybe what else? The volumetric benchmarking is the same. It's going to be quite hard, I think, maybe feasible, but quite hard to scale. And the randomized benchmarking for 1 and 2 qubit gates is okay, but higher dimensionality, it scales exponentially, essentially, which is not great. And so there are variations of this randomized benchmarking that I didn't get to mention here, like the mirror randomized benchmarking, that are a bit easier to scale up in terms of dimensionality. And most of these are generic in terms of like which type of architecture you execute them on. So you can execute most of them in any quantum computer.
Excellent. Yeah, Paul Escofet, can you speak?
Do you hear me?
Yes, Paul, go ahead.
Okay, thanks, Alejandro. It was very, very interesting. So I actually have a question regarding randomized benchmarking. So as I have understood, it's just a technique for you to obtain the median or the best fidelity for each one of the gates that you can actually execute. My question is, can you somehow guess which type of error do you have? If you have a bit error or a phase error or like a more complex error like a depolarizing one?
Yeah, I see. So actually, because of the specific nature of randomized benchmarking, in which we are, again, averaging over all types of errors and turn them into like one type of error, we cannot distinguish with just this where the errors come from, only the average error that we have transformed in this way. So it's a way to compare gates between, again, within the same device and between devices, but just by itself, it doesn't allow us to figure out where this error comes from. We need a few more advanced techniques to figure that out.
I see. Thank you.
Yeah. Yeah. So I have a last question. So you moved over to the control department. Yes. Can you tell us more about what your particular contribution to this is?
I see. Not sure how much I'm allowed to disclose publicly, but
okay. No, okay.
I got, yeah.
Okay, don't worry. I think Andres, let me activate allow mic. Yeah, Andres. Yeah, Andres, you can speak.
Okay, do you hear me?
Yes.
Okay. First of all, thank you very much for your nice presentation. I think that it was really interesting. I have a couple of questions regarding the capabilities of the chip. One of them is that if you support or you will support intermediate measurements in the future, because I think that you have not mentioned, and the only thing is that you put that you support OpenQuasm 2.0 that initially is not supporting this capability.
Yeah, so okay, so I believe OpenQuasm 2.0 is already, you can already execute as well circuits from it. And I would check our public GitHub. I think all of the software that we have public available is there. But in principle, from what I understand, I hope I'm not wrong about this, it should already be a thing that you can execute directly from OpenQuasm. And regarding the other question about intermediate measurements, I also believe that is coming if it's not there yet. But I will also have to double check with product people regarding this. But it's something that definitely any user will want.
Yeah.
Okay, I have a second question regarding the active initialization of the qubits. This means putting all the qubits to 0.
Yeah.
Do you have a specific protocol to do that, or you just wait for relaxing the qubits?
Yeah. I'm thinking how to answer this because it's a bit more involved than that. So as long as we are low enough in temperature, it is our qubits are mostly in the ground state. That is known fact. I know that there are certain active initialization protocols that will allow you to essentially reset the qubits to a better ground state. I believe those are not there yet, but I will have to again double check what is the way that it's done. And what else? At the end of the day, you can also do techniques for post-processing the data such that this doesn't matter much. So on the algorithmic execution side, this can be, I guess, fixed as well.
Okay, thank you.
Any further question? Okay, so then I think we will wrap up here and finish this nice talk. I said the first one after the summer break. So thanks a lot, Alejandro. I must say it's a little bit. It was this part of this technical problem is that you see the name on the screen of Alejandro is the name of our system manager. That so we had some problems of authorization but he's Alejandro. It's not Javier. So, but we can sort this out. So stay tuned. We'll be back the 24th of September with Pablo Bermejo, and so the series will continue with very interesting seminars. And so, goodbye, everybody, and see you soon.
Okay, thank you, everyone.
Thanks, Alejandro. Goodbye.